Hi, folks. Today I'm going to talk about how numbers are represented internally by MATLAB. So this is referred to as the machine representation of a number. As you might guess, it turns out to be rather more complicated than you'd like it to be. But it's something that you kind of have to know in order to understand how the computer will behave under certain circumstances, right? In edge cases and extreme cases. So just as a motivating example for this, just to try to convince you that this is useful to know, here's an example. Here's a little MATLAB code. It's a while loop. So what we do is we initialize the variable I to be 0, and then we're going to increment it. Every time through the loop, we will increment it by a 0.1. Okay, so we start off I is 0. While I is less than 1, right, as long as I has a value less than 1, we perform the loop. We increment I by inc, right, which is 0.1. And then we display the value of I, right? So each time through the loop, it's going to display the current value of I. Now, look at this, and before running it, tell me, well, predict what you think is going to happen, right? What do you think is going to happen? What exactly will be printed out? And then try it out, and enter these lines into MATLAB, try it out yourself, see what happens, and see if it does what you think it would do. Well, here's what it does. Anybody predict this? I'm guessing that some of you computer science majors may have guessed this, because it is kind of predictable in a sense. But what happened was that it seems to have printed an extra value of I that it shouldn't have, right? It printed the value I equals 1.1. Now, that's puzzling because after all, the line before, it printed the value I was equal to 1. When I is equal to 1, this condition in the while loop here is not satisfied, right? This is violated, and therefore the loop should not be executed. I should not be incremented. Instead, the whole thing should end at that point. So you would have thought that this would be the last value printed, but in fact, it incremented I one more time. It executed the loop one more time. Does that mean it didn't think that 1 was, it thought that somehow 1 was less than 1? Is that possible, right? That it thought the value of I was less than 1, even though it printed the value of I here, right? So what's going on? Well, the basic issue is that probably, as most of you know, numbers are represented internally in a computer in base 2, not in base 10. So I think most of you know that, right? It's kind of an old saw nowadays. The computers only understand on and off, right? They only understand binary signals. It's something is true or false, it's 0 or 1, right? So a number system in which each digit is either 0 or 1 is the most natural kind of number system to use in a computer. You could also argue that base 2 is actually the simplest number system for doing arithmetic, right? It has a very small multiplication table and addition table, right? It's very easy to learn how to do arithmetic in base 2. There are other reasons it's not convenient to teach, to use for humans. Like, for example, a body temperature would be a 6-digit number, and the boiling point of water would be a 7-digit number if we use base 2. That's not really that convenient. So, but nevertheless, for a computer, it makes a lot of sense on a lot of levels to use base 2. Okay, now let me refresh your memories. I'm assuming not everybody has thought about base 2. You probably learned the bases at some point in grammar school or high school or something, but you're probably rusty, so let me remind you. First of all, let me remind you how base 10 works, right? So base 10, our system, consider a number like 142.5. Well, the first digit, the 1 here, means that there's one component of 10 squared, right? The way it works is that the first position is the power 0, and the second position is the power 1, and the third position is the power 2. So this is one copy of 10 to the second power, right? The 4 means that there are 4 copies of 10 to the first power, and the 2 in this position tells you that there are 2 copies of 10 to the 0 power. That's actually just 1, right? The 5 after the decimal point tells you that there's 5 copies of 10 to the negative 1 power. So the powers keep going on. They get smaller by 1 as you move to the right. And so if there were a second decimal place, that would be copies of 10 to the negative 2, right? So then you combine all these. We got 1 copy of 10 squared, 4 copies of 10 to the first, 2 copies of 10 to the 0, that's just 2, and then 5 copies of 10 to the negative 1, which is 1/10. So 5 copies of 1/10, that's 1/2. So that's where the 0.5 comes from, that's 1/2. So you add them all up, and that's the value of the number. Well, base 2 works exactly the same way, except that the base of the powers are 2's, and the digits can only be 0 or 1. Now this gets harder to keep track of when you have this many digits, but basically we've got a 0 power, a 1 power, a 2 power, a 3 power, a 4 power, a 5 power, a 6 power, and a 7 power. So the 1 here tells us we have 1 copy of 2 to the 7th. We have no copies of 2 to the 6th, 2 to the 5th, or 2 to the 4th. Then we have 1 copy each of 2 to the 3rd, 2 to the 2nd, and 2 to the 1st, right? And then we have no copies of 2 to the 0, and then after the decimal point there's a 1, that tells us we have 1 copy of 2 to the negative 1. That's 1 over 2, that's 1/2, right? So then you add these all up, we get 2 to the 7th is 128, 2 to the 3rd is 8, 2 to the 2nd is 4, 2 to the 1st is 2, 2 to the negative 1 is 0.5. It actually gives us exactly the same number that we had in base 10. It's equal to 142.5 in base 10, right? Just some other quick examples. The number 10 in base 2, well, that's one way to think of it is you can think about what powers of 2 do you have to add up in order to get 10? Well, you'd have to add 8, which is 2 to the 3rd, and you'd have to add 2, which is 2 to the 1st. So therefore, 10 in base 2 would have a 1 in the 2 to the 3rd position, a 1 in the 2 to the 1st position, and zeros elsewhere, right? So it would be 1, 0, 1, 0. Right? Notice we put a subscript 2 to indicate that that's in base 2. The number 5 you would get by adding a 4 and a 1, right? So that would be 0, 1, 0, 1. Notice that the digits look very similar in 10 and in 5 because 10 and 5 differ by a factor of 2. Well, just as in base 10, it's easy to multiply numbers by 10, in base 2, it's easy to multiply numbers by base 2. You just add a 0, right? So to multiply 5 by 2, I just add a 0 and slide all the digits over to the left, right? And that gives me the representation of 10 in base 2. So in the particular case of the while loop we were looking at, the problem is the base 2 representation of the increment 0.1, right? So that's the problem. So let's see what is the base 2 representation of 0.1 or 1/10, right? How do we represent that number in base 2? There are various ways to do this. I thought I would do it by carrying out long division in base 2, kind of practice for working with base 2. So I convert the numbers to base 2. 1 is just 1, but 10 is 1010 in base 2, right? And now we're actually going to calculate this ratio using long division, right? So I'm going to divide the number 1010 into the number 1, and I'm going to use all the usual rules of long division, although as you'll see, long division is easier in base 2 than it is with ordinary numbers, because you don't have to do any real multiplication as you usually do when you're doing long division, because you have to multiply the quotient you have currently times the divisor, right? And you have to do subtracting. Everything is easier in base 2. So anyway, let's see. Let's carry it out. We can't bring in one factor of 1010 until we get to the 4th decimal place. Okay, so we get 1010, we subtract, we're left with 00110. Then we have to go down another decimal place, we can bring in another factor of 1010, and you subtract and you get this. And you'll notice that at this point we've got a just 1 here in the remainder, and so it's going to start repeating because we're just doing the same thing over again, right? We've got the same divisor into basically the same dividend 1, right? And so we're going to start repeating. This is going to produce a repeating decimal in base 2. So, although 1/10 is a nice terminating decimal in base 10, 0.1, in base 2 it's a non-terminating repeating decimal, right? So that's, they're always a little awkward to work with, that when you're, even if you're just using a calculator, repeating decimals are kind of a pain because the calculator will always truncate them and you never get the exact value. So the same thing is happening with 0.1 in the computer. So internally, 0.1 is represented by a truncated number because it can't represent all infinitely many of the repeating digits. It just truncates it at a certain point. And therefore, the truncated value that's stored in the computer is actually slightly less than 0.1, right? And that means after you sum up 10 copies of that increment, right, you don't quite get 10 times 0.1, which would be 1. You actually get something that's slightly less than 1. And that means that the while condition in the loop, this condition here, is actually still satisfied the 10th time through the loop. And therefore it executes this loop one extra time until I becomes almost 1.1, not quite 1.1, but at that point it's at least certainly bigger than 1, and therefore this condition is no longer satisfied and we exit the loop, right? But only after having executed the loop one extra time, one time more than we thought it was going to. MATLAB by default uses 64 bits to store numbers. You can actually get custom representations, so you can have 32-bit numbers and maybe even 128-bit numbers, I'm not sure. But the default seems to work well enough, certainly for our purposes. So I'm just going to talk about the 64-bit format, but there other formats are available. So this means that they use a string of zeros and ones, 64 bits long, in order to represent numbers. So if you wanted to represent positive and negative integers using 64 bits, a very easy and natural way to do it would be to say, let's take the first bit to represent the sign of the number. So if the bit is 1, we'll think that the number is positive, and if the bit is 0, we can interpret that as meaning the number is negative. And then you have 63 bits left to store the binary representation of the number, right? The largest number you could store that way would be all 1. So the sign bit would be 1, so it's positive, and then you'd have 63 ones following that. And that number would be equal to, well, let's see, one way to think about that is if you had a 1 in the next position over and then all zeros and subtracted 1, you would get exactly this left, right? So you take a 1 in the 64th position on the left, zeros elsewhere, subtract 1, and you would get a sequence of 63 ones. This 1 in the 64th position actually represents 2 to the 63rd power, because remember, we start counting at 0 down here. So this number, 63 ones here, that actually represents 2 to the 63rd minus 1. Right, so the largest number you'd be able to represent using this scheme would be 2 to the 63rd minus 1, and then of course you can also represent negative 2 to the 63rd minus 1, just change the sign bit to a 0. Now, that seems pretty good, pretty natural and simple, but there is a slight inefficiency. It seems pretty minor, it seems trivial actually, but it's the kind of thing that, computer scientists obsess about. They want to squeeze the maximum amount of usage out of the memory that they're using. You notice that 0 is represented in two different ways, because if you have all zeros in this position here, right, the value is still 0 regardless of whether the sign is positive or negative, right? So positive and negative 0 are really representing the same number. Also, you cannot actually represent the number 2 to the 63rd. The highest you can go up to is 2 to the 63rd minus 1. So, what's actually usually used is a slightly different scheme that allows you to both express 2 to the 63rd, and it doesn't have this inefficiency of representing a 0 in two different ways. The penalty for doing this is that the scheme is a little more complicated. Well, a little less transparent, let me put it that way. It's a little less transparent. So what we do is we'll be able to represent any number from negative 2 to the 63rd plus 1 to positive 2 to the 63rd, we will use all 64 bits. We do not have a sign bit in a sense. I'll comment on that in a minute. What we do is we take whatever number n that we want to represent, and instead we represent the number n plus 2 to the 63rd minus 1. And then we represent this number using 64 bits. Right? So, for example, take the number 2 to the 63rd. That number in binary would have a 1 in the 64th position. That would be this position on the extreme left here, and we have zeros elsewhere. Right? All the remaining 63 digits would all be zeros. Then you add 2 to the 63rd minus 1 to it. That number in binary consists of 63 ones. Right? You add them up, and what you get is 64 ones. So this number, 64 ones, it actually represents the number 2 to the 63rd, and it looks like the number 2 to the 64th minus 1. How would you represent the number 1? Well, if you take the number 2 to the 63rd minus 1 and add it to 1, you get 2 to the 63rd. The ones cancel. And so that would consist of a 1 in the 64th position, right? That represents 2 to the 63rd here, and all the other numbers would be 0. So this would be the number 1. What does the number 0 look like? Well, the number 0 would just have 0 followed by 63 ones, right? Because n would be 0, so this number would just be represented by 2 to the 63rd minus 1. It would be 63 ones, but the first bit would be a 0. What would minus 1 look like? Well, you add minus 1 to this, and what you're doing is you're taking 2 to the 63rd minus 2. Well, you just cancel the 1 from the bottom, right? Another way to think about it is take the 0 and subtract 1. So if you subtract 1 from this, you're just changing that last bit from a 1 to a 0. So this would be negative 1. And what's the smallest number you can enter? Well, negative 2 to the 63rd plus 1, represented this way, would be represented by all zeros, right? Because everything would cancel in this expression. You just get 0, and therefore that number would be represented by 64 zeros. Now, there is another way to think about this, which I find kind of helpful sometimes, although you might find it confusing, so feel free to ignore this if you don't like it. But you could say that the first bit still represents the sign, in the sense that if the first bit is a 1, that means the number is positive. And if the first bit is a 0, that means the number is either negative or 0. Right? So 0 is the only non-negative number that begins with a 0. Right? The remaining 63 bits tell you the value of the number. Peculiarity is that positive numbers are represented in those 63 bits not by n, but by n minus 1. Right? So, for example, if you look at the 63 bits up here, right, over here, you got 63 ones there. That's not 2 to the 63rd. That's 2 to the 63rd minus 1. In a similar way, the number 1 is represented by 63 zeros. Right? It's got a 1 in the sign bit, so it tells you it's a positive number, but it's represented in the remaining 63 bits by all zeros, so that's actually represented by 1 minus 1, right, and so on. And then here's another peculiarity. Non-positive numbers are represented by reversing the zeros and ones. So, for example, negative 2 to the 63rd, well, it's a negative number, so it should have the first bit should be 0 to say it's not a positive number. Positive 2 to the 63rd minus 1 would be all ones. So because this is a negative number, you reverse the zeros and ones, and it's all zeros. Right? This is a kind of a convenient way. It does make it, this trick does make it somewhat easier to come up with a representation for negative numbers. You just represent the positive number and then reverse the zeros and ones. So I find it a helpful trick. You may not. Feel free to ignore this. That still leaves us with two big problems. We also want to be able to represent non-integers, right? We have to be able to work with decimals and fractions and everything. And the biggest number you can store using as a 64-bit integer is 2 to the 63rd power. And that's actually not very big. If you work it out, it's only about 9 times 10 to the 18th, right? Which is not an astronomical number, right? So if you're an astronomer, for example, that's not going to cut it for you. You'll need to be able to work with bigger numbers. Another one I just looked up was Avogadro's number from chemistry. It's 6 times 10 to the 23rd. So again, if you're a chemist, if you're working with large numbers like that, 64-bit integers aren't actually going to do it for you. But we can solve both problems, representing non-integers and representing very large numbers, with a similar trick. What we can do is we can make use of basically scientific notation. So recall scientific notation, I actually used it here, right? 9 times 10 to the 18th. In base 10, scientific notation works by taking a number from 1 to 10 and multiplying it by a power of 10. Right? So any number can be represented this way, by some number from 1 to 10 times a power of 10. In the computer, we'll do it in a similar way. We'll represent numbers using scientific notation, except, of course, everything is base 2, so we will pick numbers, a number that's between 1 and 2 times a power of 2. So take an example. Take the number 10. We know that that's equal to 1010 in base 2, right? We saw that earlier. But you could write that in base 2 using scientific notation as 1.01 base 2 times 2 to the third power. So multiplying by the 2 to the third tells you that you have to move the decimal place 3 places to the right, to make it a bigger number. So instead of 1.01, it becomes 1010. So altogether now there's going to be 3 pieces to our representation. We're going to have a sign bit, right? So we're going to go back to that. We're going to have a sign bit. We're going to have an exponent bit or set of bits. And then we're also going to have what's called the significand, and that is this number out front, right? In our case, it's going to be a number between 1 and 2, right? And we have to be able to represent that. And most of the bits are actually going to be for the significand. So somehow they came up with a scheme that they use 1 bit for the sign, which of course isn't the normal way to do it. You only need 1 bit for the sign, and it's either positive or negative, right? So if the sign bit is 1, we interpret that as meaning the number is positive. If it's 0, we interpret that as meaning the number is negative. I guess through experimentation, trial and error, finding out what worked, it seemed that they decided on 11 bits for the exponents seemed to work well enough, right? So of the 64 bits, because we're still working with 64 bits of storage space for a number, of those 64 bits, we're going to reserve 11 bits to represent the exponent of the number, right? This power of the number up here. Now, the power itself could be either a positive or negative number, because using scientific notation, you can represent very large numbers if you have a positive power, but you can also represent very small numbers that are close to 0 if you have a negative exponent, right? So the exponent is going to itself can be either positive or negative. So we've got 11 bits to represent basically an integer that could be the positive or negative. So what we're going to do is we're going to use a scheme analogous to the one we were just describing on the previous slide. That is, on the previous slide, we had a way of representing numbers, integers in 64 bits. Now we're going to represent integers in 11 bits. Right? It's just going to represent the power of the number, right, for the 2 to the what power. And so replace all the 64s in the previous scheme by 11 and replace the 63s you see by 10. So the way the power will be represented is if you have a power p, like in this case p was 3, so if you have a power p, we're going to represent it by adding 2 to the 10th minus 1 to that p. 2 to the 10th minus 1 is actually 1023. So we're going to take p plus 1023, and we'll represent that number using the 11 bits. Or you can think about it in terms of the my second explanation. I think I'll skip that here, but so those of you who like that, you can think of it that way. But basically, we're following the second method we described previously. Okay, and then that leaves 1 bit for the sine, 11 bits for the exponent. That leaves 52 bits left over that we can use to describe the significand, right, which is this part here, right, the number between 1 and 2 that we multiply the time into the power. Now, in the case of the number 10, the sign is 1 because it's a positive number. The exponent is 1, 0, 0, 0. How many zeros? I guess I got 8 zeros there, and then ending in 1, 0. Right? If you like, you can think of that using my second scheme. It's like the first digit tells you that the number is positive, and then the remaining 10 digits represent the power minus 1. Right? 3 minus 1 would be 2. Right? Or you can think of it using this scheme. The power was 3. We add 1023 to 3, so this is the number 1026 represented in binary notation. Right? And then finally, for the significand, we have 52 bits to represent the number 1.01. Now, here's the thing. All of these numbers will always begin with a 1 point something. So we don't need to write the 1 point, right? We can leave that. We can omit that because it's always present. So what we do instead is we just write the decimal part. So we just write the decimal part with the understanding that we are supposed to prepend a 1 point to these digits. Right? So this string of zeros and ones represents the number 1.01000000. Right? So that's how the significand works. It's 52 bits that represent only the decimal part of the significand. Okay, let's look at some examples, because this, as you can imagine, gets rather confusing. So, as we just saw, the number 10 can be represented in this format by 1 in the sign position, by the number 1026 in the exponent position. 1026, that's the actual exponent of 3 plus 1023 is how we represent the exponent 3. And then the significand for 10 was 1.01, which we represent as only the decimal part 0, 1, 0, 0, all zeros from there on. Right? Now the number 5 would be very similar to the number 10 because it's exactly 1/2 of the number 10, and therefore it can be represented exactly the same way as the number 10, except that we change the exponent, we reduce the exponent by 1. Right? So here the exponent was 3, here the exponent would be 2. So for 5 the exponent is 2, which is represented as 1025. Right? So this would be 1025. Or you could just say take this representation of the exponent and subtract 1 for it to get the representation for the exponent for 5. Right? But the significand would be exactly the same for 5 as it was for 10. Right? Only the power of 2 differs. Negative 5 would be represented by, in exactly the same way as positive 5, we just changed the sign bit, right? Just change the sign bit from 1 to 0. Now, what about this number 0.1 that caused us trouble earlier? How is that represented in this format? Well, first of all, we saw when we did the long division and worked it out in base 2, it's equal to 0.000110011 repeat, right, in base 2. So in scientific notation, we can think of that as 1.1001 repeat, basically. The 1001 gets repeated forever. And then this is times 2 to the negative 4th. It tells us that we should move the decimal place 4 places over to the left to get this number. Right? So the sign is positive, so the sign bit is positive. The power is negative 4, so that gets represented as negative 4 plus 1023 would be 1019, right? 1019. So this is 1019 in binary notation. And the significand gets represented only by the decimal part, so that's this, the 1001001 repeat. And of course, we can't give all infinitely many repeating digits, we just give the first 52 of those digits. Right? That's all you're able to do. And again, because of that, it's truncated, and the value of 0.1 in the computer is not quite as big as the true value of 0.1, right? We left off the last, the 53rd, all the digits from the 53rd on. Right? Now, looking at some big numbers we can represent, the number 2 raised to the 1023 can be represented. Well, this is obviously the significand is 1 point all zeros, right? So the significand is all zeros. The power is 1023. Now, if you take 1023 and add 1023 to it, you get 2046. So this is the number 2046 in binary, right? I've written 1022 here because you can also think that the last 10 digits represent the number 1022, which is 1023 minus 1. Right? So remember, that's an alternate way of thinking about this representation. And of course, the sign is positive, right? So this is a large number, which you represent by having a large exponent, right? Let's see. We can increase the value by increasing the significand, right? So if we keep the exponent exactly the same, the largest we can increase the significand to would be this, and this number would represent 1.11111 repeat. Now, if you actually took 1.111 and repeated the 1 forever, that would be like 9.999 repeat. It would actually be equal, which is actually equal to 10. 1.1 repeat would actually be equal to 2. This is not quite that, because we don't have all infinitely many digits, but this is actually 2 to the minus 52nd less than what would be 2 in the significand, right? So it's as if you took 2 in the significand and subtracted off 2 to the minus 52nd. That would leave you with this value, 1.11152 times. So this number here actually represents 2 times 2 to the 1023, which would be 2 to the 1024, except we subtracted off 2 to the minus 52. So this is the largest number you can represent without increasing that power. Okay? Now, there's still a problem. Even after all that work, there's still a problem. We don't have a way to represent 0. Think about it. The significand always has an implicit 1 point something, prepended to it. So how do we represent 0 if we're always going to prepend a 1 point to the representation of the significand? Even if we put all zeros here, this still represents 1, right? So we don't seem to have a way to represent the number 0, so we have to do something about that. So there's going to be an exception to this format in order to be able to represent 0. So 0 will be represented by the number, or by the binary representation, a 1, or actually a 0, because it wouldn't. The sign of 0 doesn't really matter, so you could have either a 1 or a 0 here. But then all the remaining 63 bits would be zeros, right? Now that's how 0 is represented, but notice that this constitutes an exception to the format we've just been describing. Normally, a number with these bits would represent, let's see, let's take it one at a time. The exponent bits are all 0, so normally that would represent power 2 to the negative 1023. But for one thing, there's an exception that when the exponent is all zeros, it doesn't represent the power negative 1023, it represents the power negative 1022. Okay, that's one exception. A more important exception for representing 0 is that when the exponent is 0, like this, then all zeros like that, then we do not prepend a 1 point to the significand bits. We prepend 0 point to the significand bits. So, second exception, because the exponents bits are all 0, we prepend 0 point to the significand bits. So then this represents 2 to the negative 1022, but times 0, not 1. Okay? So as another example, suppose you had the number 1 in the sign bit, all zeros in the exponent bit, and then you had all zeros except a 1 at the very end in the significand bits. So because the exponent bits are all 0, we're in this exceptional situation, and the power would be a negative 1022 instead of negative 1023. And furthermore, because we would prepend a 0 point to the significand bits, this number would simply represent 2 to the negative 52. Right? Not 1 plus negative 2 to the negative 52, but just 2 to the negative 52. And so you multiply these together, in scientific notation, so to speak, and this would represent the number 2 to the negative 1074. That is actually the smallest positive number that can be represented in this format. Right? It's the smallest number greater than 0 that can be represented using this 64-bit floating point format. So, just to reiterate, in general, when the power is all zeros, or in other words, the exponent bits are all zeros, then, contrary to the usual rules for the format, the power is 2 to the negative 1022, and we multiply by not 1 point, but 0 point, followed by all the significand bits. Okay? So that's one exception. There's another exception coming up. Sorry about that. So the other exception occurs at the other extreme value for the exponent, when the exponent is its maximum value. So when the exponent is all ones, normally you would expect that to represent an exponent of 1024. Right? However, instead, it's used to represent 3 different non-numbers, really. They're non-real numbers, or pseudo-numbers or something. So they're used to represent plus or minus infinity, or not a number. NaN, if you see that, means not a number. It's when you get a result that cannot be assigned a numerical value, even in principle. Right? So, for example, 0 divided by 0 is not a number, it's just an undefined quantity, right? And if you do weird things like if you try to multiply a number times a string, I think you'll get not a number, right? If you do things that don't make any sense, you'll get not a number. Infinity, you get when you divide a non-zero number by 0, right? So 3 divided by 0 is positive infinity, negative 3 divided by 0 is negative infinity. But you can also get infinity if the operation produces a number that's too large to be represented in the given format, right? So, for example, if I take 2 to the 600th divided by 2 to the negative 600th, that would actually give me 2 to the 1200, right? However, the power of 1200 is too big to be represented in this format because the highest conceivable power would be 1024. So power of 1200 is just too big. So in this case, we have a number that cannot be represented, and so rather than just represent it by the highest possible number, we want to signal that we've run out of our capacity to represent the number. So we're going to call that number now infinity. So the number infinity is represented by the 64-bit representation when the exponent bit is all ones, but when the significand is all zeros. It's completely zero. Okay? And then you can have positive or negative infinity depending on the sign bit, right? But infinity is characterized by the exponent bits being all ones and the significand bits being all zeros. Right? So this would be negative infinity when the sign is 0, and this would be positive infinity when the sign is 1, right? When the sign bit is 1. Right? When the significand is not all zeros, if there are any non-zero bits in the significand, then that's considered not a number, right? But it's also occurs when the exponent bits are all ones, right? So exponent bits are all ones signals that this number is going to be either plus or minus infinity or not a number, right? So in this case, the exponent bits are all 1, the significand is not all 0, so this is not a number. And then just for completeness, I also included the exception when the exponent bit is all zeros, then and the significand is all zeros, this just represents the number 0. In this case, it doesn't even matter what the sign bit says, right? Notice that the sign bit would matter if the significand was not all zeros, right? Because you could have a small positive number or a small negative number with a significand that's not all zeros. So we were just looking at some limitations on our ability to represent numbers in MATLAB. So we saw that the largest numbers you can represent in MATLAB are on the order of 2 to the 1023rd power, right? If you try to represent numbers larger than that, MATLAB will just tell you it's infinity, right? And similarly, you can't represent negative numbers that are smaller than that. Another important limitation on your ability to represent numbers is when you consider the increment, the smallest possible increment between numbers. So for example, here are two numbers that are almost identical. They're represented by almost identical strings of 64 bits. The only difference between them is in the very last bit. One of them is 0, the other is 1. In particular, they have the same sign and the same power. In this case, the power represents a power of 3, right? So both numbers have exponential factors of 2 to the 3rd. And that means that the difference in the significands, this difference in the very last digit of the significand, represents a difference between the values of the numbers of 2 to the negative 52 times 2 to the 3rd, right? Because everything gets multiplied by the exponent 2 to the 3rd, right? What you could say is that this means that the second number is about 2 to the negative 52 larger than the first number in relative terms, right? That it's this fraction of the first number larger than to get the second number, right? The second number is this fraction of the first number added to it again to get the second number. So you could say that this number 2 to the negative 52 it's an important quantity in describing limitations of MATLAB's representation of numbers, that you cannot increment by a relative amount smaller than 2 to the negative 52, because this is the smallest change you can make in two numbers, right? This is called the machine epsilon, right? So computer languages and I guess software and hardware, I don't know anything about hardware really, but I'm guessing hardware too also has this kind of limitations. But the machine epsilon represents this a kind of a fundamental limitation on your ability to increment numbers, right? To go from one number to the next higher number. In general, you can define the machine epsilon for any language or computer package or whatever by saying it's equal to the smallest possible increment you can make to the number 1, right? So 2 to the negative 52 is the smallest possible increment we can make in MATLAB to these 64-bit floating point numbers. That would give us a number that registers as being greater than 1. If we try to add a number smaller, a positive number smaller than 2 to the negative 52nd to 1, MATLAB will just tell us the result is still 1. It won't know what to make of this smaller number, right? So this represents a fundamental limitation on our ability to do things, to do incremental computations in MATLAB. So this will come up later when we're doing integrals and things, when we're trying to work with very small numbers, and we want to, for example, integrate by looking at small integrals of x values along the x-axis, right? We have to keep in mind that there are limitations in what we can do in performing this kind of numerical integration. This will be a significant issue.